Introduction: a window into the cosmos in the quiet stillness of the night. When the world falls silent and the stars begin to shimmer in the deep canvas of the sky, we are gently reminded of a truth as old as time itself. We are part of a vast, mysterious universe. Cosmology is the science that dares to ask the grandest of all questions: where did it all begin? What is the universe made of? How does it evolve? And where, if anywhere, is it going? This journey into cosmology is not merely a scientific endeavor. It is a voyage of the soul. It begins with wonder, fueled by curiosity, and guided by careful observation and imagination. Throughout history, humans have looked to the heavens, first with naked eyes, then with telescopes, and now with space-based observatories that see across every wavelength of light. Each new lens has revealed something extraordinary: that the universe is far larger, stranger, and more beautiful than we ever imagined. Cosmology rests upon a foundation of observations, patterns in the night sky, echoes of ancient light, subtle motions of galaxies, and whispers from particles we can barely detect. These observations, often gathered from the faintest signals, allow us to construct a story of the cosmos from its fiery birth to its uncertain fate. They are the building blocks of knowledge in a universe that refuses to give up its secrets. Easily dot in this audiobook. We will explore 20 of the most fundamental observations and concepts that shape our understanding of the cosmos. From the discovery of the expanding universe to the strange pull of dark energy, from the earliest light ever emitted to the ghost-like neutrinos passing through us, we will delve into the core ideas that define modern cosmology. Each chapter is designed to open a window, a gentle, quiet window, into one of these vast ideas. You will hear about the cosmic microwave background, the curvature of space, the mysteries of time and entropy, and even the tantalizing possibility of other universes. But this is not a lecture. It is a guided exploration, a calm and thoughtful walk through some of the deepest questions we can ask. There is no rush here, just the slow unfolding of ideas, like stars emerging one by one in the twilight sky. Whether you are already familiar with cosmology or just beginning to explore it, you are invited to listen, reflect, and wonder. The universe is waiting. Let us begin. Chapter 1: The Expanding Universe. Imagine, for a moment, the night sky above you. The stars appear still, serene, ancient. For thousands of years, humanity believed that the heavens were fixed, eternal, and unchanging. But hidden in the gentle glow of galaxies, there was a subtle shift, one that would quietly rewrite our understanding of reality. That shift, barely perceptible through a telescope, revealed a universe in motion. Not just any motion, but an expansion of space itself. The idea of an expanding universe emerged slowly, like a whispered secret carried on cosmic winds. In the early 20th century, astronomers began to notice something peculiar. Light from distant galaxies appeared redder than expected. This wasn't due to the galaxies being redder in color, but because their light was shifted toward the red end of the spectrum. This phenomenon is known as redshift, and it carried a profound implication. The galaxies were moving away from us. This discovery was not a lone observation. It was part of a growing puzzle. The first hints came from the work of Vesto Melvin Slipher, who, in the 1910s, measured the velocities of spiral nebulae and found that many were receding. But the true breakthrough arrived in 1929, when Edwin Hubble published his famous observation. The farther away a galaxy is, the faster it appears to be moving away. This relationship, now known as Hubble's law, suggested something revolutionary. The universe is expanding, not simply expanding into empty space, but stretching the very fabric of space itself. This was a difficult concept to grasp, and it remains so even today. The galaxies are not flying away through space like debris from an explosion. Rather, space itself is growing, carrying the galaxies along with it. The universe is not expanding into anything, it is expanding from within. This realization changed everything. It meant that the universe was once smaller, denser, and hotter. If we rewind this expansion, mathematically and conceptually, we arrive at a point of beginning. This became the foundation of the Big Bang Theory, a model of cosmic evolution that explains how the universe has expanded and cooled over billions of years. But expansion is not uniform. Some galaxies are held together by gravity into clusters and superclusters. Locally, gravity can overcome the expansion, allowing galaxies to dance in spirals or collide over eons. But on the largest scales, the expansion dominates. The cosmic web, vast filaments of matter stretching across spaces, growing. Reshaped by the flow of time and the push of expansion. Measuring this expansion required a standard of cosmic distance. Astronomers turned to Cepheid variable stars, whose brightness varies in a predictable way as cosmic yardsticks. Later, type Ia supernova, which explode with nearly identical luminosity, became another tool. These observations allowed scientists to refine the value of the Hubble constant, the rate at which the universe expands. Yet, even today, the exact value of the Hubble constant is a subject of debate. Measurements based on the early universe, like Those from the cosmic microwave background differ slightly from those based on the nearby universe. This discrepancy, known as the Hubble tension, could hint at new physics. Perhaps something we do not yet understand is influencing the expansion of the cosmos. The expanding universe also reshapes our notion of the cosmos's edge. There is a limit to what we can observe, the observable universe, beyond which light has not had time to reach us since the Big Bang. But due to the ongoing expansion, even regions that emitted light billions of years ago are now much farther away than when that light began its journey. One of the most poetic consequences of this expansion is the idea that in the distant future, most galaxies will disappear from view. Their light, stretched and redshifted by the swelling cosmos, will fade beyond detectability. Future astronomers may find themselves in a lonely universe, unaware of the grandeur we now see. And yet, the expansion tells a story of origin, motion, and transformation. It connects the first moments of existence to the galaxies we see today. It tells us that the cosmos is not a static painting, but a living, evolving tapestry. Each distant galaxy, each beam of stretched light is a witness to that movement, the gentle echo of the universe's unfolding. The expanding universe was the first great revelation of modern cosmology. It opened the door to new questions. What drives this expansion? Will it go on forever? Did it have a beginning? Is there an end? In the quiet pulse of red-shifted light, in the stretching of space itself, we find the rhythm of a universe in motion. And this motion, once invisible to our ancestors, now becomes the key to unlocking everything that came before, everything that may still lie ahead. Chapter 2. The Cosmic Microwave Background. In the vast silence of space, a quiet whisper lingers. It is not the sound of planets or stars, nor the distant hum of galaxies colliding. It is older, softer, fainter, and yet it holds within it the memory of the universe's birth. This whisper is the Cosmic Microwave Background, or CMBA, delicate afterglow from the moment the cosmos became transparent. To understand the CMB, we must travel backward in time. Not millions of years, nor billions, but to a time just 380,000 years after the beginning. At this early moment, the universe was a dense, hot, plasma-glowing fog of particles and radiation. Photons, the particles of light, were constantly scattering off electrons and protons. The universe was opaque, like the inside of a star. But as the universe expanded, it cooled. Slowly, like steam condensing into water, the particles lost their energy. Eventually, it became cool enough for electrons to combine with protons, forming neutral atoms. This process, called recombination, allowed light to move freely for the first time. The universe became transparent, and the photons from that moment began a journey that continues to this day. Those ancient photons are what we now detect as the cosmic microwave background, originally emitted in the visible spectrum. Their wavelengths have been stretched by the expansion of the universe, shifted into the microwave range. They now bathe all of space in a faint, uniform glow. No matter where you look in the sky, this background radiation is there, silent, persistent, and incredibly informative. The CMB was first discovered in 1965 by Arno Penzias and Robert Wilson, two radio astronomers working at Bell Labs. They weren't searching for echoes of the Big Bang. They were troubleshooting a strange noise in their antenna, background hiss that wouldn't go away. Little did they know, they had stumbled upon one of the most important discoveries in cosmology. The existence of the CMB confirmed the predictions of the Big Bang theory. Competing ideas, like the steady-state universe, could not explain this universal radiation. The CMB was the smoking gun evidence that the universe was once hot and dense, and that it has been expanding and cooling ever since. But the CMB is not just uniform noise. It contains tiny temperature fluctuations, minute differences in energy, only a few millionths of a degree. These variations are not random. They are the fingerprints of primordial density differences, the seeds from which galaxies and clusters would eventually grow. In those slight wrinkles in the fabric of the early universe lies the blueprint of everything we see today. To study these patterns in detail, scientists launched specialized missions. In 1989, NASA's COPE satellite confirmed the black-body nature of the CMB and detected its subtle anisotropies. In 2001, the WMAP mission provided a clearer map of temperature fluctuations. And in 2009, the Planck satellite offered the most precise measurements yet, revealing the age, shape, and composition of the universe with astonishing accuracy. Through the CMB, we have learned that the universe is about 13.8 billion years old. We know its curvature is nearly flat, and that only a small fraction of its contents is made of ordinary matter. The rest is invisible, dark matter and dark energy, inferred through the imprint they leave on this ancient light. The CMB also holds clues about what happened before recombination. Some theories suggest that cosmic inflation, a rapid expansion, just after the Big Bang, left imprints in the polarization of the background radiation. Scientists search for these patterns called modes as evidence of inflation and primordial gravitational waves. There is something humbling about the CMB. It is the most distant thing we can observe, not because it is far away in space, but because it is far back in time. It is the edge of the observable universe, a glowing wall that marks the boundary between darkness and light. And yet, it is everywhere. Every patch of sky, every corner of space carries this ancient signal. It is, in many ways, the universe's oldest photograph, a frozen image of the cosmos as it was in its infancy, long before stars, galaxies, or planets formed. We are looking not just across space, but across time itself, reading the first lines of the cosmic story written in radiation. And though it is invisible to our eyes, the CMB touches us. Every second, millions of these ancient photons pass through your body, whispering of a time when the universe was young and light was finally set free. It is a reminder that we are part of a story far larger than ourselves, a story that began in fire, evolved in silence, and continues to unfold with every passing moment. Chapter 3: The Big Bang Theory in the Quiet Darkness of Deep Time. The universe was once a single pointed place where all of space, all of matter, and all of energy existed in a state beyond human imagination. There was no light, no galaxies, no atoms, only an intensely hot, dense, and compressed beginning. And from that beginning, everything began to change. This idea, bold and elegant, is known as the Big Bang Theory. It is not a theory of an explosion in space. It is a theory of the expansion of space, a transformation not from a central point outward, but from a singular state into an evolving cosmos, where time and space themselves were born. The name Big Bang was actually coined sarcastically by a skeptic in a 1949 radio broadcast. Astronomer Fred Hoyle, who supported the rival steady-state model, used the term to mock the idea. Ironically, the name stuck and eventually came to represent the most successful cosmological model ever developed. The roots of the Big Bang Theory lie in Einstein's general theory of relativity. In 1917, Einstein applied his equations to the universe as a whole, and, to his surprise, they predicted a dynamic cosmos there, expanding or contracting. Uncomfortable with the idea of a changing universe, he introduced a cosmological constant to maintain stability. But years later, when Edwin Hubble discovered that galaxies were receding from us, Einstein called this correction his greatest blunder. The universe was expanding, just as the equations had originally implied. If the universe is expanding now, logic suggests that it was smaller in the past. As we reverse the cosmic clock, galaxies draw closer, temperatures rise, and matter becomes more tightly packed. Eventually, we reach a moment where everything known, every proton, photon, and atom was compressed into a nearly infinitesimal point. This moment, around 13.8 billion years ago, is what we refer to as the beginning of the universe. But the Big Bang was not a moment in space. It was the moment space began. There was no before, no empty black void waiting to be filled. Time and space were created in that first instant. It was the origin of everything, including the laws of physics themselves. What followed was an extraordinary sequence of events. In the first fractions of a second, the universe experienced a period of unimaginable rapid expansion, known as cosmic inflation. Tiny quantum fluctuations were stretched to cosmic scales, planting the seeds of future galaxies. As inflation ended, the universe reheated. Particles collided with incredible energy, forming the first basic building blocks of matter. In the next few minutes, the process of nucleosynthesis began, forging light elements like hydrogen, helium, and traces of lithium. Yet, the universe remained dark for hundreds of thousands of years. Photons, scattered by free electrons, could not travel freely. Only after recombination, when neutral atoms formed, did light break free and the cosmic microwave background was born. This unfolding narrative expansion, observations with remarkable precision. The abundance of light elements, the redshift of distant galaxies, and the uniform glow of the CMB support the Big Bang model. But despite its successes, the theory does not answer everything. It does not explain why the universe began, or what, if anything, came before. It does not describe the singularity itself, the point of infinite density at time zero, because our current physics breaks down there. The Big Bang is a beginning, but not a complete explanation. It is a map of cosmic evolution, not a story of ultimate origins. Questions remain. Why does the universe appear so flat and uniform? What caused inflation? What is the true nature of dark energy and dark matter? Still, the Big Bang theory remains our best description of the universe's early history. It tells a story of simplicity becoming complexity, of particles becoming stars, and of silence becoming song. A story that continues with every supernova, every swirling galaxy, and every human gaze lifted to the sky. In a very real sense, we are children of the Big Bang. The atoms in your body were once part of that primordial fire. The iron in your blood was forged in ancient stars whose ancestors trace their roots to that first blinding moment. The Big Bang lives in us as we live in its aftermath, and as we listen to the cosmos, decoding its ancient light and subtle vibrations we come a little closer to understanding not just where we are, but how we came to be. Chapter 4: The Composition of the Universe. When we gaze into the star-filled night sky, it's tempting to believe we are seeing the entirety of the cosmos. Countless stars, luminous galaxies, and glowing nebulae stretch across the vastness of space. And yet, astonishingly, everything we console the planet's stars, and gas makes up less than 5% of the universe. The true composition of the cosmos is a story of hidden realms and unseen forces. It is a story in which the familiar is just a sliver of a much grander whole, and where the vast majority of existence is invisible, silent, and deeply mysterious. Let's begin with the known. Ordinary matter, also called baryonic matter, is the stuff of atoms, protons, neutrons, and electrons. It forms stars and galaxies, dust and gas, people and planets. It is the matter that emits or reflects light, making it detectable through telescopes across all wavelengths, from visible light to X-rays and radio waves. But as cosmologists measure the gravitational behavior of galaxies and galaxy clusters, a strange discrepancy emerged. There was not enough visible mass to account for the motions they observed. Galaxies rotated too fast, clusters held together too tightly. Something unseen was exerting a gravitational pull. This invisible mass was named dark matter. It does not emit, absorb, or reflect light. We cannot see it directly, but we can observe its effects. Dark matter acts as a cosmic scaffold, shaping galaxies and large-scale structures through gravity. Without it, the universe, as we know it, would not exist. Estimates suggest that dark matter makes up about 27% of the total energy density of the universe. Its nature remains one of modern cosmology's greatest puzzles. Is it composed of exotic particles like WIMPs, weakly interacting massive particles, or ixions? Could it be explained by modified gravity instead of matter? These are open questions, and experiments deep underground and in space continue the search. Even more mysterious than dark matter is dark energy, a term that represents approximately 68% of the universe. This strange component was discovered not by looking at what pulls the universe together, but by studying what pushes it apart. In the late 1990s, two teams of astronomers observing distant Type Ia supernova made a startling discovery. The expansion of the universe was accelerating. Instead of slowing down under gravity's pull, galaxies were being pushed away from each other at an increasing rate. Some unknown force was causing this acceleration. That something was named dark energy. It appears to be a property of space itself, a repulsive force counteracting gravity on cosmic scales. It is smooth diffuse, and unlike anything else we know. The simplest explanation ties it to Einstein's once abandoned cosmological constant, a term he introduced to stabilize his equations. Others propose more dynamic forms, such as quintessence or evolving scalar fields. Dark energy remains elusive, yet its presence is necessary to explain the observed structure and fate of the cosmos. It dominates the energy balance of the universe, shaping its large-scale geometry and influencing its ultimate destiny. Putting it all together, the composition of the universe can be summarized as 5% ordinary matter baryons, 27% dark matter, 68% dark energy. This balance has been determined with remarkable precision through observations like the cosmic microwave background, baryon acoustic oscillations, galaxy surveys, and the Hubble diagram of supernova. Each piece of data acts like a puzzle fragment, pointing to the same conclusion. The universe is mostly made of things we cannot see. Even the ordinary matter contains mysteries. It includes visible stars and gas, but also dark clouds, rogue planets, and faint brown dwarfs. Some of it is locked away in black holes. Much of it is spread thinly across the cosmic web, difficult to detect but essential to cosmic evolution. And still, we are left with a profound sense of humility. The universe we know, the one we study and inhabit, is just the tip of a much larger iceberg. The vast majority lies hidden in shadow, accessible only through its gentle pull or its quiet push. The light of galaxies is a whisper. The dark is the song. This composition, strange and uneven, invites deeper questions. What is dark matter, truly? What drives dark energy? Are there other components still undiscovered? And how do they all interact to shape the past, present, and future of the cosmos? In learning what the universe is made of, we also learn what we are made from and what we are not. We are the rare, visible shimmer in an ocean of darkness. Yet from that shimmer, we observe, we ask, we wonder, and slowly, piece by piece, we illuminate the unseen. Chapter 5: The Geometry of the Universe. We often think of space as a vast, silent void, boundless backdrop against which galaxies drift and stars ignite. But space is not merely an empty canvas. It has shape, structure, and geometry. The way light travels, the fate of the cosmos, and the nature of gravity all depend on the very fabric of space itself. To understand the geometry of the universe, we must first accept a revolutionary idea. Space is not flat by default. Its shape depends on the contents of the cosmoson, the balance between energy, matter, and the expansion rate. Geometry in the cosmic sense, is not just an abstract mathematical notion. It is the reality in which all things move. There are three fundamental geometric models that scientists consider when describing the large-scale structure of the universe. Flat geometry, Euclidean. In this model, space extends forever in all directions. Parallel lines never meet, and the angles of a triangle always add up to exactly 180 degrees. This is the intuitive geometry. Most people are familiar with the universe that behaves like a gigantic flat sheet. Light travels in straight lines, and the expansion may continue forever depending on the contents of the universe. Closed geometry, spherical. Here, space is curved like the surface of a sphere. Parallel lines eventually converge and triangle. Angles add up to more than 180 degrees. Such a universe is finite in volume, but has no edges, like walking in one direction on Earth and eventually returning to your starting point. If the mass energy density is high enough, gravity slows and eventually reverses the expansion, leading to a potential big crunch. Open geometry, hyperbolic. This shape resembles a saddle or a Pringle chips base curves away from itself. Parallel lines diverge, and triangle angles add up to less than 180 degrees. In this model, the universe expands forever, and the rate of that expansion accelerates, creating a cold, sparse future. Which of these geometries describes our universe? To answer this, cosmologists needed precise measurements of large-scale cosmic structure. One key clue came from the cosmic microwave background, CMB. As we saw earlier, this ancient light carries subtle variations in temperature and density. By analyzing the angular size of these fluctuations, especially a feature known as the first acoustic, peak scientists could infer the overall curvature of space. The results were surprising in their clarity. The measurements from satellites like WMAP and Planck suggest that the universe is remarkably flat, with only the tiniest margin of error. This means that on the largest scales we can observe, the geometry of space appears Euclidean. But how can this be? For the universe to be flat, its total energy density must be incredibly close to a critical value. Too much matter, and it curves inward. Too little, and it curves outward. Achieving flatness requires a kind of cosmic fine-tuning, something that puzzled scientists for decades. This mystery gave rise to the theory of cosmic inflation. During the universe's earliest moments, a rapid exponential expansion could have smoothed out any initial curvature. Inflation explains not only the flatness problem, but also the uniformity and structure of the cosmos. It suggests that our observable universe is just a tiny patch of a much larger and potentially more complex multiverse still. Even in a flat universe, space can be dynamic. The geometry tells us not only about shape, but also about destiny. A flat universe with only matter would eventually slow its expansion. But in our case, dark energy dominates, and it drives an accelerated expansion. The universe will continue to stretch indefinitely, galaxies drifting ever farther apart, stars dimming, and time stretching endlessly forward. The geometry of the universe also governs how light bends and travels. Gravitational lensing the distortion of background. Light by massive objects gives us a way to measure curvature indirectly. In a curved space, light follows the contours of gravity, weaving paths that can create arcs, rings, and multiple images of the same galaxy. These effects are not just visual curiosities. They are precise tools for probing the shape of space-time, even the structure of the cosmic web, the vast network of galaxies and voids stretching across the cosmoses. Shaped by this underlying geometry, the way galaxies clump, how filaments connect, and how large-scale structures evolve are all tied to the rules that geometry imposes. We live, then, not in a formless expanse, but in a universe with mathematical character where shape defines destiny, and curvature whispers secrets about the past and future. To ask about the geometry of the universe is to ask something deeply poetic. What is the shape of everything? What is the form of the infinite? Are we living in a boundless plane, a closed sphere, or something stranger still, perhaps beyond our perception altogether? For now, all signs point to flatness. But as our instruments grow more sensitive and our minds more open, we may yet uncover deeper layers of cosmic shape ripples in dimensions, folds in time, and edges we once thought didn't exist. Chapter 6: The Expanding Universe and Redshift. There was a time when astronomers believed the universe was static and changing, eternal and fixed in space. The stars appeared unmoving in the night sky. Galaxies were thought to be part of our own Milky Way, and the cosmos, in its vast silence, seemed immutable. But that vision began to crumble in the early 20th century, when a quiet revolution unfolded in the observatories of Earth and in the equations of Einstein's general relativity. The universe, it turned out, was not still. It was expanding. That discovery would change everything we thought we knew about time, space, and destiny. The first hints came from a phenomenon known as redshift. Light, like sound, can be stretched or compressed depending on motion. When a source of light moves away from an observer, its waves are stretched, increasing their wavelength and shifting toward the red end of the electromagnetic spectrum. This is called Doppler redshift, and it's the same effect that lowers the pitch of a receding train whistle. But what astronomers discovered was something even more profound. Their light was consistently redshifted, and not just slightly. They were moving away from us at speeds proportional to their distance. The farther the galaxy, the faster it receded. This observation became known as Hubble's law, and it revealed that the universe itself was expanding. Not because galaxies are flying through space like shrapnel from an explosion, but because space itself is stretching, carrying galaxies apart with it. This expansion affects everything on the largest scales, the light traveling through space. The distance between clusters, even the cosmic clock by which we measure time. The cosmological redshift is a direct result of this expansion. As light travels through the stretching fabric of space, its wavelength lengthens. Unlike Doppler redshift, this is not due to motion through space, but to the expansion of space. The photon is literally stretched as it journeys across the cosmos. This redshift serves as a kind of cosmic ruler and cosmic clock. By measuring how much the light from distant objects has shifted, astronomers can estimate how far away those objects aren't, how long ago their light was emitted. In this way, telescopes become time machines, allowing us to look back billions of years and witness galaxies as they were when the universe was young. The expansion is not uniform in every respect. On smaller scales within galaxies, solar systems, an atom's gravity and other forces dominate, and the stretching of space is imperceptible. But on cosmic scales, between galaxy clusters and filaments of the cosmic web, the universe flows outward like a tide that never ebbs. Redshift also plays a key role in tracing the universe's history. The cosmic microwave background, for instance, was once blindingly hot and bright. But over billions of years, its light has redshifted into the microwave part of the spectrum, cooled by the stretching of space itself. What was once a roaring fire has become a faint, whispering glow. Even more astonishing is the discovery that the expansion is accelerating. Distant supernovae appear dimmer than expected, implying they are farther away than they should be in a uniformly expanding universe. This means that some mysterious force, now called dark energies, pushing the universe outward faster and faster. The redshift we observe today is not merely a remnant of the Big Bang, but a signal of an ongoing, deepening transformation. Different redshift values correspond to different epochs in cosmic history. A redshift of Z equals 0 is the present day. Z equals 1 corresponds to when the universe was about half its current age. Z equals 10 takes us to a time when galaxies were first forming. And the highest redshifts, above z equals 13, offer glimpses into the cosmic dawn, when the first stars ignited and brought light to the darkness. The expanding universe, revealed through redshift, is not just a discovery, it is a revelation. It tells us that the cosmos has a past, that it evolves, and that it had a beginning. It allows us to measure time, not by the ticking of a clock, but by the stretching of starlight. It shows us that everything, galaxies, atoms, even space itself, is part of a grand, dynamic unfolding. There is a quiet poetry in redshift. The farther we look, the redder the light becomes. The older the signal, the more stretched and softened it is. And yet, in that faint and reddened glow, we find the stories of galaxies born, stars exploding, and time itself expanding into silence. We live in a universe that is not still, but alive, with motion drifting, accelerating, unfurling, like a flower that never stops blooming. Chapter 7. The Cosmic Microwave Background. Imagine the universe as a newborn, hot, dense, and filled with light. A searing fog of energy and particles, too chaotic for atoms to form, too bright for the darkness of night. For hundreds of thousands of years after the Big Bang, this opaque sea of radiation was all there was. No stars, no galaxies, only an endless glowing plasma. But then, something changed. Around 380,000 years after the universe's birth, it cooled just enough for the first atoms, mainly hydrogen, to form. As electrons joined with protons, the charged particles that once scattered photons became neutral. Suddenly, the universe became transparent. Light could travel freely for the first time. That light has been traveling ever since, stretched by the expansion of space, fading from a white-hot blaze to a faint, cold whisper. This light is the cosmic microwave background, the CMB. It is the oldest light we can observe, a remnant of the universe's infancy, and one of the most powerful tools in cosmology. It is not a spotlight, but a soft, uniform glow that fills the entire sky, coming from every direction. A signal from a time before stars, before galaxies, before even the first darkness, discovered accidentally in 1965 by Arno Penzias and Robert Wilson. The CMB presented itself as an unexplainable background noise, a persistent microwave hiss that came from no particular source. They had stumbled upon the echo of the Big Bang, a discovery that would win them the Nobel Prize and revolutionize our understanding of the universe. The CMB is remarkably uniform, with a temperature of just 2.725 Kelvin, lonely a few degrees above absolute zero. Yet it contains tiny fluctuations, differences in temperature on the order of millions of a degree. These minute ripples hold the keys to the cosmos. Why are they so important? Because they are the seeds. The slight overdensities in the CMB map correspond to regions where gravity would slowly pull matter together, eventually forming stars, galaxies, and entire clusters. Without those fluctuations, the universe might have remained featureless, vast expanse of perfect uniformity. Instead, the cosmos evolves structure, variety, and life. Modern satellites like COBE, WMAP, and Planck have mapped the CMB with extraordinary precision. These observations have produced a kind of baby picture of the universe, revealing patterns that match predictions from theories of inflation, matter composition, and cosmic expansion. From these maps, scientists can extract fundamental data. The age of the universe, about 13.8 billion years, the curvature of space essentially flat. The density of ordinary matter, dark matter, and dark energy, the rate of expansion, known as the Hubble constant, the early physics of sound waves in the primordial plasmies. Even sound, though not in any form we could hear. The early universe behaved like a vast drum, with pressure waves oscillating through the hot plasma. These baryon acoustic oscillations are visible as characteristic peaks in the CMB's power spectrum and offer another cosmic ruler to measure large-scale structure. But the CMB is not static. As technology improves, we find more detail. Polarization measurements offer insights into the scattering effects of primordial particles and even hint at the influence of gravitational waves, ripples in space-time, caused by inflation in the very first instant of the universe, in a very real sense. The CMB is a cosmic fossil frozen in time, preserving the universe's earliest memory. And like a fossil, it tells a story not of bones or stone, but of temperature, symmetry, and light. It tells us how the universe transitioned from chaos to order, from blinding radiation to starlit space. There is also something deeply poetic in this ancient glow. It connects us to a moment when time itself was still young, when light had just been freed from its bondage, and when the cosmos was taking its first quiet breath. Every photon of the CMB has been traveling for nearly 14 billion years uninterrupted. It has passed through galactic voids, skirted around galaxies, and finally arrived to our detectors, our instruments, and our minds. When you look up into the night sky, remember, beyond the stars and the blackness lies this soft afterglow, a quiet echo from the dawn of everything. Chapter 8: Large-Scale Structure and the Cosmic Web. When we look up at the night sky. We often see stars as solitary, point-isolated lights suspended in darkness. Even galaxies, from our vantage point, appear scattered like cosmic islands floating through the abyss. But this view, as vast as it seems, is still narrow. If we could zoom out far beyond the scale of individual stars or galaxies, past the realm of clusters and voids, we would see a different kind of cosmos emerge. A structure so immense and interconnected, it resembles something biological like the filaments of a brain, the strands of a spider's web, or the branches of ancient roots stretching across unimaginable distances. This is the cosmic web, large-scale structure of the universe. The cosmic web is a vast, three-dimensional network of filaments, sheets, and voids, formed by the gravitational pull of dark matter and the dynamics of expanding space. It is not a metaphor. It is the actual scaffolding of the cosmos, a delicate yet powerful structure upon which galaxies are strung like pearls, and clusters gather at the intersections. But how did such structure arise? The answer begins with the fluctuations in the cosmic microwave background, those subtle temperature differences we explored in the previous chapter. In the early universe, some regions were slightly denser than others. Gravity, persistent and patient, began to amplify these differences. Over billions of years, these overdensities attracted matter, forming long chains and nodes of galaxy clusters. The underdense regions, where matter was scarce, became cosmic voids, vast, empty spaces where few galaxies reside. Today, we map this architecture through massive surveys of the sky. Projects like the Sloan Digital Sky Survey, SDS, have cataloged millions of galaxies, allowing astronomers to build three-dimensional maps that span billions of light years. What they reveal is breathtaking. A universe woven together with galaxies tracing out an intricate, almost organic pattern across space. At the heart of this structure lies dark matter, the invisible substance that makes up most of the matter in the universe. Although we cannot see it directly, its gravitational influence shapes the behavior of visible matter. Think of dark matter as the invisible scaffolding upon which the luminous parts of the cosmos stars and galaxies assemble. Supercomputer. Simulations like the Millennium Simulation and Illustris have allowed us to model this cosmic architecture. These simulations start with early universe conditions based on CMB observations and evolve the universe forward in time under the influence of gravity and expansion. The result: webs of filaments and knots that mirror what we observe in deep sky. Surveys: the nodes where multiple filaments meet are the richest environments in the cosmos. These are the galaxy clusters, massive conglomerations of hundreds or even thousands of galaxies bound together by gravity. Here, galaxies interact, merge, and evolve in dynamic, high-density environments. The filaments are like intergalactic highway streams of dark matter and gas that funnel material into clusters. Galaxies within these filaments often share properties, such as similar star formation rates or orientations. Shaped by the flow of matter through these structures, and then there are the voids. Expanses so large and empty they defy comprehension. Some voids stretch for hundreds of millions of light-years, containing only a few faint galaxies, like whispers in a cosmic silence. These are not failures of creation, but expressions of balance. Where matter gathers, there must also be places it recedes from. The cosmic web is not static. It is in constant motion, though on timescales far beyond human life. Filaments stretch and evolve, clusters collide, and galaxies fall into gravitational wells. In this slow dance, the universe shapes, itself driven by invisible forces and ancient ripples of energy. This structure holds more than aesthetic beauty. It tells us about the content of the universe, the nature of dark matter, and the initial conditions after the Big Bang. It also acts as a lens, bending light from distant sources through gravitational lensing, offering yet another way to study both visible and invisible matter in many ways. The cosmic web reflects a kind of universal symmetry, order emerging from chaos, structure from randomness, connection amid distance. It reminds us that the universe is not merely a collection of isolated objects, but a unified system, interdependent, evolving, and shaped by forces beyond what we can see. To know the cosmic web is to grasp the vastness not only of space, but of structure, a realization that everything, our Milky Way, our solar system, even ourselves, resides within the thread of this grand tapestry, moving silently within a framework that has been forming since the dawn of time. Chapter 9: Dark Matter and its Gravitational Role. There is a shadow woven into the fabric of the universe. It cannot be seen. It does not shine, reflect, or emit light. Yet its presence is undeniable, felt in the movements of galaxies, in the bending of starlight, and in the grand architecture of the cosmos. This invisible component is known as dark matter, and though it escapes direct detection, it holds the key to understanding how the universe truly works. The first clues to its existence came from something rather ordinary: how galaxies spin. In the 1970s, astronomer Vera Rubin studied the rotation curves of spiral galaxies according to Newtonian mechanics. But Rubin found something surprising. The outer stars weren't slowing down. In fact, they were orbiting at nearly the same speed as the inner ones. This discrepancy suggested that something unseen was contributing mass something that extended far beyond the visible edges of the galaxy. The term dark matter was used to describe this missing mass. And the universe hasn't looked the same since today. Scientists estimate that about 27% of the universe's total energy content is made of dark matter. In contrast, all the atoms that form stars, planets, and people account for less than 5%. The remaining portion, as we'll see in future chapters, is attributed to dark energy. But what exactly is dark matter? That remains one of the most profound mysteries in physics. It is not made of ordinary atoms. It doesn't interact with electromagnetic radiation, hence its darkness. It seems to exert influence only through gravity, pulling on other matter, shaping the paths of stars and galaxies, and bending light that passes nearby. But despite its powerful presence, it does not collide, clump, or glow. It is silent in every sense except gravitationally. Several theoretical particles have been proposed to explain it. One leading candidate is the Wimpa-Weakly interacting massive particle. These hypothetical particles would interact via the weak nuclear force and gravity, making them hard to detect but potentially discoverable in highly sensitive underground. Experiments. Another possibility lies in ixions, ultralight particles that could form a diffuse field throughout space. There are even more exotic suggestions, like primordial black holes, supersymmetric particles, or modifications to the laws of gravity themselves. But regardless of its true nature, the effects of dark matter are everywhere. Without it, galaxies could not have formed the way they did. In the early universe, dark matter clumped first, creating gravitational wells that drew in normal matter. These wells served as the seeds from which galaxies grew. In large-scale simulations, dark matter forms the skeleton of the cosmic web, with filaments of invisible mass guiding the flow of gas and galaxies. Its role is not merely to exist, is to shape. Through gravity, it influences the motion of stars, the dynamics of clusters, and the distribution of matter on cosmic scales. We also observe dark matter indirectly through a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the path of light around them. When we observe distant galaxies whose light is warped or duplicated, we can infer the presence of intervening dark matter, even when no visible mass is seen. In this way, dark matter leaves fingerprints on the fabric of space-time itself. And yet, for all this influence, dark matter remains elusive. Despite decades of research and ingenious experiments from deep mines to space-based detectors, no particle has been conclusively identified. It hides in plain sight, shaping the stars. Yet, avoiding our touch, there is a certain beauty in this cosmic mystery. Dark matter reminds us that not everything that exists can be seen. Some truths are felt through their effects, sensed by the way they move the world around them. Just as wind reveals itself through rustling leaves, dark matter is known by the curves of galaxies and the arcs of ancient light. In time, perhaps we will uncover its nature. We may build the instruments precise enough to detect a signal, or stumble upon a theory that explains its silence. Until then, we look out at a universe wrapped in shadow, and we listen not with ears, but with minds open to what gravity tells us. Chapter 10: Dark Energy and the Accelerating Universe. For most of human history, the cosmos was imagined as static, eternal, and unchanging. Even after we discovered that galaxies are receding from one another, that space itself is stretching, there was still an assumption gravity would eventually slow this expansion. Like a ball tossed into the air, it might keep rising for a while, but surely it would fall back, slowed by the pull of its own weight. But the universe had another surprise. In the late 1990s, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam, set out to measure the rate of cosmic expansion by observing Type Ia supernova. These stellar explosions are considered standard candles, meaning they have a known intrinsic brightness. By comparing how bright they appear from Earth, scientists can determine their distance, and with it, the history of cosmic expansion. What they found was unexpected, almost unbelievable. The distant supernovae were dimmer than anticipated because they were farther away in a slowing universe. But because the universe had been accelerating in its expansion, instead of gravity slowing the cosmic growth, something was speeding it up. This force unknown, invisible, and pervasive was dubbed dark energy today. Dark energy is thought to make up nearly 70% of the universe's total energy content. It's not matter, and it's not radiation. It doesn't clump or gather. It seems to be inherent to space itself, a property of the vacuum that pushes space apart. But what exactly is it? One idea is that dark energy is a modern reappearance of Einstein's cosmological constant he introduced and later abandoned to allow for a static universe in his equations of general relativity. The cosmological constant behaves like a uniform energy density that fills all of space, creating a repulsive pressure that drives acceleration. Another possibility involves scalar fields, dynamic energy fields that evolve over time. These models, often referred to as quintessence, imagine dark energy as a changing entity, possibly tied to the conditions of the early universe or to the fate of the cosmos itself. The effects of dark energy are profound. It governs the geometry and destiny of the universe in a universe without dark energy. The expansion would eventually slow, potentially reverse, and collapse into a big crunch. In a universe dominated by dark energies, ours appears to be expansion not only continues but accelerates, making galaxies recede faster and faster as time goes on. This means that, over the course of billions of years, galaxies, not gravitationally bound to ours, will drift so far away that their light will no longer reach us. The sky will grow darker, more silent. The cosmic web will dissolve into isolated islands, separated by ever-widening gulfs of empty space. And yet, despite its dominance, dark energy is among the least understood aspects of the universe. It does not behave like any known particle or field. It seems to defy the logic of thermodynamics and quantum mechanics. Even its energy scale is a puzzle 120 orders of magnitude smaller than predictions from quantum field theory. This vast mismatch is known as the cosmological constant problem, one of the greatest unsolved questions in physics. Some scientists wonder whether dark energy is even a thing at all, rather a sign that our understanding of gravity itself is incomplete. Could general relativity require modification at cosmological scales? Might dark energy be an illusion born of deeper, unknown laws? Observational efforts continue with projects like the Dark Energy Survey, the Euclid Space Telescope, and the Nancy Grace Roman Space Telescope, aiming to refine our measurements. By studying galaxy clusters, gravitational lensing, and the large-scale structure of the universe, cosmologists hope to unlock dark energy's secret. But for now, it remains a cosmic enigma, silent force that dictates the tempo of the universe's expansion, shaping its future with a quiet hand. There is something humbling in this. We often imagine the universe as driven by fire and gravity, by collisions and explosions. Yet here is a force that works in stillness, that hides in the vacuum, and that ultimately may decide the fate of everything. Dark energy is not loud. It is not violent. It simply is expanding space itself, pulling galaxies apart and whispering through the void with the power of infinity. Chapter 11: The Hubble Constant and the Expansion Debate. In the early 20th century, our understanding of the cosmos underwent a dramatic transformation. For centuries, the universe was believed to be static, eternal, and unmoving. But then came a series of observations that changed everything, culminating in the discovery that space itself is expanding. This expansion is not a movement through space, but a stretching of space itself. And like all motion, it can be described. with a read a measure of how fast distant galaxies are receding from us as a function of their distance. That rate is known as the Hubble constant. The story of this constant begins with Edwin Hubble, who, in 1929, published a seminal paper showing that galaxies farther away are receding faster. By measuring their redshifts, how much their light is stretched, and comparing that to their distance, he found a linear relationship, now known as Hubble's law. The constant of proportionality in that law is what we now call h0, the Hubble constant dot at its core. The Hubble constant answers a seemingly simple question: how fast is the universe expanding today? But as our measurements have become more precise, the answer has become more complicated. In recent decades, cosmologists have used two main methods to determine age, and strangely, they don't agree. The first approach is direct measurement, often referred to as the cosmic distance ladder. This method starts with nearby stars whose distances are known precisely through parallax measured shifts in their positions as Earth orbits the Sun. From these first rungs, astronomers calibrate the brightness of Cepheid variable stars and type Ia supernova, allowing them to estimate the distances to faraway galaxies. Comparing these distances to redshift yields a value of the Hubble constant. This method, championed by researchers like Adam Rees, consistently yields a value of around 73 to 74 kilometers per second per MEG APARSEC. The second approach is more indirect. It relies on measurements of the cosmic microwave background, CMB, the afterglow of the Big Bang. The Planck satellite, which studied this ancient light in exquisite detail, allows cosmologists to infer the value of the Hubble constant by fitting the data to the standard model of cosmology known as CDM lambda, cold dark matter. This model includes parameters for dark matter, dark energy, and the initial conditions of the universe. The result: a lower value, about 67.4 kilometers per second MPC. This difference may seem small, but the gap is statistically significant. It has only grown. More puzzling as measurements on both sides have improved in precision. This disagreement is known as the Hubble tension, and it has become one of the most talked about challenges in modern cosmology. It suggests one of two possibilities. Either there are unaccounted for errors in our measurements, or there's something missing in our understanding of the cosmos. Could new physics be at play? Some theories propose exotic early universe particles or variations in dark energy over time. Others suggest modifications to gravity on large scales, or that the universe is more complex than the simple CDM model allows. Still others posit unknown interactions between known components, like dark matter decaying or neutrinos behaving unexpectedly. Meanwhile, new techniques are emerging. Observations of gravitational waves, ripples in space-time from colliding black holes or neutron stars on an entirely different way to measure cosmic distances. These events could become standard sirens, analogous to supernova, but based on the timing of gravitational waves. Adding another rung to the ladder, the upcoming James Webb Space Telescope and missions like Euclid and Nancy Grace Roman promise to sharpen our understanding even further. As more data comes in, cosmologists hope to resolve the tension or perhaps uncover something wholly new at its heart. The debate over the Hubble constant is more than a numbers game. It's a window into the deep structure of the universe. The value of h influences estimates of the universe's age, the size of cosmic features, and the timing of galaxy formation. A shift in this number echoes across every scale of cosmic evolution. There is beauty in this uncertainty. It reminds us that even with all we've learned, the universe still holds surprises. The Hubble tension may one day be resolved through deeper understanding, or it may point to the dawn of a new physics. Whatever the outcome, the pursuit continues. Quiet telescopes, silent sky, and questions that stretch across light years. Chapter 12. The Observable Universe and its Horizon. When we gaze up at the night sky, we look not only outward into space, but also backward in time. Each point of light, each shimmering star or distant galaxy, is a message from the past. Its photons having traveled for millions or even billions of years before reaching our eyes. This simple truth leads us to one of the most profound concepts in cosmology: the observable universe. It is not the universe in its entirety, but the region of space from which light has had time to reach us since the beginning of the cosmos. According to our best measurements, the universe is approximately 13.8 billion years old. One might then assume that the farthest we can see is 13.8 billion light-years away. But the expansion of space complicates this intuition. As space itself stretches, the light traveling through it is redshifted, its wavelength elongated by the growing fabric of the cosmos. This means that while a photon may have left its source billions of years ago, the actual distance to that source today is greater than the time it took for the light to arrive. When this stretching is accounted for, the current radius of the observable universe is estimated to be about 46.5 billion light-years in every direction. This creates a spherical region around us, roughly 93 billion light-years across a bubble within which every galaxy, star, and particle is visible in principle, provided they emit or reflect enough light. Beyond that bubble lies the unobservable, not empty, not non-existent, just beyond our reach. The light from those regions has not yet had time to arrive, and perhaps never will, depending on the universe's future. This boundary is called the cosmic horizon, limit not of existence, but of perception. It's important to understand that this horizon is observer-dependent. Every observer, no matter where they are in the universe, will have their own observable bubble centered around them. It's not that we are at the center of the cosmos, but that we are at the center of our own light cone, defined by the speed of light and the age of the universe. The observable universe is filled with structured galaxy clusters, voids, filaments woven into a grand tapestry shaped by gravity and time. And at its farthest edges, we find the cosmic microwave background, CMB, a faint afterglow from about 380,000 years after the Big Bang, when the universe first became transparent. This light marks the edge of visibility, the limit of electromagnetic information. But are there things beyond the observable universe? Almost certainly. The inflationary model of cosmology, the leading theory of how the universe expanded in its earliest fractions of a second, suggests that the universe is much larger than we can observe. Perhaps infinite, perhaps part of a multiverse. But if light from those regions has not yet reached us, we remain forever separated by cosmic speed limits. Interestingly, there are galaxies currently within our observable universe whose light we can see today, but which are receding faster than light due to the expansion of space. This doesn't violate relativity, because it's space itself expanding motion through space. In time, their light will redshift into oblivion, and those galaxies will disappear from view, their photons never reaching us again. This gives rise to the concept of a cosmic event. Horizon at deeper limit, defined not by what we can see now, but by what we can ever hope to interact with in the future. Galaxies beyond this horizon will never send light that reaches us again. They are not just far, they are forever out of touch. There is something both humbling and poetic about this. The observable universe is not just a sphere of matter, and energy is a sphere of knowledge, a finite window onto the infinite. It contains everything we can ever study, explore, or know directly through observation. And yet, it may be just a tiny fraction of a reality far grander in that sense. We live inside a cosmic lighthouse, our beacon of awareness limited by time, distance, and the laws of nature. But through mathematics, theory, and imagination, we can reach beyond even those borders. The horizon is not the end of the universe. It is simply the edge of our understanding. Chapter 13. The Cosmic Microwave Background. Light from the Infant Universe. Before stars, before galaxies, before even the first atoms had formed, the universe was a hot, dense sea of particles, plasma of light and matter so tightly bound that photons could not travel freely. In this early state, the cosmos was opaque, like the interior of a glowing furnace. But that would soon change. Roughly 380,000 years after the Big Bang, something extraordinary happened. The universe cooled. Enough for electrons and protons to combine and form the first neutral hydrogen atoms. This process, known as recombination, marked a profound shift in the universe's structure. With no more free electrons to scatter light, photons were suddenly free to travel great distances unimpeded. That moment released a flood of radiation. In all directions, the oldest light we can observe, echoing across the cosmos like a fossilized whisper. That light is the Cosmic Microwave Background, or CMB. Today, we detect this ancient radiation as a faint microwave glow spread uniformly across the sky. It is not bright or dramatic. Its temperature is a chilly 2.725 Kelvin, just above absolute zero. Yet within its soft glow lie clues to the birth and structure of the universe. First detected accidentally by Arno Penzias and Robert Wilson in 1965. The CMB was a triumph for the Big Bang theory. At the time, many still considered the steady-state theory, which claimed the universe had no beginning and remained unchanged over time. But the discovery of the CMB provided concrete evidence that the universe had, indeed, begun in a hot, dense state. Over the decades, scientists have mapped the CMB with increasing precision. Instruments like COBE, WMAP, and Planck have revealed that this background radiation is not perfectly smooth. It contains tiny fluctuations, differences in temperature and density at the level of 1 part in 100,000. These minute variations are not imperfections. They are seeds. They are the imprints of quantum fluctuations stretched to cosmic scales. During the brief but explosive period of inflation, these initial ripples in the early universe would later grow under the pull of gravity into galaxies, clusters, and cosmic filaments, the vast structure of the universe we see today. By analyzing these fluctuations, cosmologists have been able to determine the universe's age, its composition, and its curvature. The CMB confirms that the universe is made up of roughly 5% normal matter, 27% dark matter, and 68% dark energy. It supports the view that space is geometrically flat on large scales, and that the universe underwent a dramatic period of inflation in its earliest moments. The CMB is also a time capsule photograph of the universe when it was just a baby. It allows scientists to peer back nearly 14 billion years, far beyond what any telescope could see using visible light. No star or galaxy is older than the CMB. It is the limit of vision, the primordial glow that lights up the edge of the observable universe. Even more remarkable, the CMB is not just evidence of what happened. It is a cosmic benchmark that every new theory must respect. If a model of the early universe doesn't match the patterns and anisotropies seen in the CMB, it is ruled out. In this way, the CMB is both ancient and modern discovery that continues to shape the cutting edge of cosmology. New efforts seek to extract even subtler information from this ancient light. Scientists are searching for the imprint of primordial gravitational waves, ripples in space-time that may have been generated during inflation. If detected, these waves would leave a distinct signature in the polarization of the CMB, offering a glimpse into physics at energy scales far beyond any laboratory on Earth. In this sense, the CMB is more than light. It is a message from the beginning, a soft, omnipresent glow that carries within it the memory of a universe just awakening. It is not heard in sound or speech, but in microwaves, numbers, and patterns that stretch across the heavens. As we continue to study it, we listen more closely to that message, hoping to understand not just how the universe began, but why it looks the way it does today. In the darkness of space, the cosmic microwave background shines not as a beacon, but as a gentle reminder. The universe remembers its own birth, tells the story patiently in the language of light. Chapter 14: Galaxy Formation and the Cosmic Web. The night sky is filled with countless stars, grouped into magnificent islands of light called galaxies. These vast collections of stars, gas, dust, and dark matter are the building blocks of the visible universe. But how did these colossal structures come to be? To understand galaxy formation, we must begin with the early universe. Just after the cosmic microwave background released its first photons, the tiny fluctuations in density, imperceptible ripples in the primordial plasma began to grow under the influence of gravity. Imagine a landscape of hills and valleys, where matter is drawn toward the valleys regions with slightly higher density. Over millions of years, these overdensed areas attracted more and more matter, collapsing and merging into larger clumps. This gradual gathering of matter led to the birth of the first dark matter halos invisible, massive structures made of dark matter that serve as gravitational wells. Though dark matter does not emit or absorb light, its gravity pulls in ordinary matter. gas, and dust. Within these halos, gas cooled and condensed, eventually igniting the first stars. These early stars, often massive and short-lived, enriched the surrounding gas with heavier elements through their explosive death supernova, setting the stage for future generations of stars and the formation of galaxies. Galaxies themselves rarely form in isolation. Instead, they assemble along vast filaments of matter, stretching across hundreds of millions of light-years. These filaments, interconnected in a grand tapestry known as the cosmic web, outline immense void regions almost empty of galaxies. The cosmic web is a natural consequence of the initial conditions seeded by inflation and shaped by dark matter and gravity. Galaxies cluster at the nodes of this web, forming groups, clusters, and SUPRCLUST. Within this structure, galaxies evolve through mergers and interactions. Some collide and combine, triggering bursts of star formation. Others fall prey to tidal forces, stripping away gas and stars. Our own Milky Way is part of a small group of galaxies, located on a filament extending from the larger Virgo supercluster. Different types of galaxies spiral, elliptical, irregular, flecked. Their histories and environments. Spirals, like the Milky Way, have graceful arms of young stars and gas, while ellipticals are often older, redder, and more spherical, shaped by past collisions. The formation of galaxies is also intimately linked to the mysterious dark matter and dark energy. Dark matter scaffolds the cosmic web, providing the gravitational backbone. Dark energy influences the universe's expansion, affecting how galaxies move and cluster over cosmic time. Studying galaxy formation helps us understand not just where we are in the universe, but how the universe has evolved from a hot, smooth beginning to a richly structured cosmos filled with stars, planets, and potentially life. Modern telescopes, from Hubble to the James Webb Space Telescope, peer deep into space and time, observing galaxies as they appeared billions of years ago, when the universe was young and galaxies were just forming. Through these observations, cosmologists test their theories, refining our picture of cosmic history. The story of galaxies is a story of gravity, gas, stars, and dark matter woven together in a cosmic dance that continues today and shapes the vast and beautiful universe we call home. Chapter 15. Dark Matter, the invisible sculptor of the cosmos. Imagine a universe where the stars, planets, and galaxies we see are only the tip of a colossal iceberg, where the vast majority of matter remains unseen, invisible to our instruments, yet exerting a profound gravitational influence. This is the universe we inhabit, dominated not by ordinary matter, but by the mysterious substance known as dark matter. The concept of dark matter arose in the early 20th century when astronomers noticed discrepancies between the visible mass of galaxies and the gravitational forces required to hold them together. In the 1930s, Fritz Zwicky studied galaxy clusters and found that their visible matter was insufficient to explain the high speeds of individual galaxies within the clusters. He proposed the existence of dunkel materie, or dark matter. Later, in the 1970s, Vera Rubin observed the rotation curves of spiral galaxies and found that stars in the outer regions orbit much faster than expected based on visible mass alone. The implication was clear. There must be an unseen mass providing additional gravitational pull. Dark matter does not emit, absorb, or reflect light, hence the name dark. It interacts with normal matter only through gravity, making it elusive to direct detection. Yet, dark matter makes up approximately 27% of the universe's total mass energy content, vastly outweighing the roughly 5% made up of ordinary atoms. This invisible substance acts as the scaffolding for cosmic structure. Galaxies form within vast halos of dark matter, which draw in gas and dust through gravity. Without dark matter, the intricate cosmic web and the galaxies it supports might never have formed. Scientists have proposed various candidates for dark matter particles, including WIMPs, weakly interacting massive particles, axions, and sterile neutrinos, but so far, direct detection has remained elusive despite sophisticated experiments deep underground and in space. The existence of dark matter is supported not only by galaxy rotation curves and cluster dynamics, but also by its fingerprints on the cosmic microwave. Background fluctuations and the patterns of gravitational lensing, the bending of light from distant objects by massive dark matter concentrations. Gravitational lensing allows astronomers to map the distribution of dark matter, revealing vast halos surrounding galaxies and clusters, as well as the large-scale filaments of the cosmic web. Understanding dark matter is essential not just for cosmology, but also for fundamental physics, as it points to new physics beyond the standard model of particle physics. Some alternative theories propose modifications to gravity, but these have yet to explain the full range of observations as successfully as the dark matter hypothesis. In essence, dark matter is the invisible sculptor of the cosmos, shaping the universe's structure silently and invisibly. As research continues, future experiments and observations may finally unveil its nature, opening a new chapter in our understanding of the cosmos. Until then, dark matter remains a profound mystery, a shadow in the universe that guides the dance of galaxies and the evolution of all cosmic structure. Chapter 16: Dark Energy and the Accelerating Universe in the Grand Cosmic Story. There was a surprising twist near the turn of the 21st century of discovery that challenged our deepest assumptions about the fate of the universe. For decades, astronomers believed that the expansion of the universe, set in motion by the Big Bang, would gradually slow down due to the pull of gravity from matter both visible and dark. But precise observations of distant supernova revealed something unexpected. The universe's expansion is not slowing, but accelerating. This acceleration implies the presence of a mysterious force permeating space itself, a force pushing galaxies apart with increasing vigor. Scientists call this force dark energy. Dark energy constitutes roughly 68% of the total energy content of the universe, making it the dominant component today. Despite its prevalence, dark energy remains one of the greatest enigmas in physics. Unlike matter, dark energy does not clump or cluster. It appears uniform and constant throughout space, exerting a negative pressure that drives cosmic acceleration. One simple explanation for dark energy is the cosmological constant, introduced by Einstein in 1917 to achieve a static universe, then abandoned after the discovery of expansion. The cosmological constant represents a fixed energy density of empty space, or the vacuum energy. However, theoretical estimates of vacuum energy from quantum physics overshoot observational values by an astonishing 120 orders of magnitude, a staggering discrepancy known as the cosmological constant problem. Other theories propose dynamic fields, like quintessence, that evolve over time, or modifications to general relativity on cosmic scales. Dark energy influences the universe's ultimate fate. If it remains constant or grows stronger, galaxies will move apart ever faster, stars will exhaust their fuel, and the cosmos will approach a cold, dark, and lonely Big Freeze. Alternatively, if dark energy changes, it might lead to different endings, from a big rip, tearing apart all matter, to a gentle slowing and possible recollapse. Dark energy also affects the formation and clustering of cosmic structures. It competes against gravity, shaping the large-scale distribution of galaxies and voids. Observations from space telescopes, galaxy surveys, and the cosmic microwave background continue to refine our understanding, seeking clues in the universe's expansion, history, the discovery of dark energy has revolutionized cosmology, turning our view of the cosmos upside down and highlighting how much we still have to learn. It is a reminder that the universe is full of surprises and that the darkest mysteries can lie not just in distant shadows, but in the very fabric of space itself. Chapter 17: The Formation and Evolution of Stars. Stars are the luminous beacons scattered throughout the cosmos, the fundamental building blocks of galaxies, and the forges where the elements essential to life are created. But how do stars form, and what is their journey through the vastness of space? The story begins in vast, cold clouds of gas and dust, known as molecular clouds or stellar nurseries. These clouds, often spanning light years across, are composed mainly of hydrogen, with traces of helium and heavier elements under the influence of gravity. Regions within these clouds begin to contract and collapse. As the gas compresses, it heats up, forming dense pockets called protostars. When the core temperature of a protostar reaches about 10 million degrees Kelvin, nuclear fusion ignites. Hydrogen atoms fuse into helium, releasing an enormous amount of energy that counterbalances gravity's inward pull. This delicate balance marks the birth of a main sequence star, the longest phase in a star's life. Stars come in a vast range of sizes and masses. Their mass determines their brightness, temperature, lifespan, and fate. Massive stars burn hotter and brighter, but live shorter lives, while smaller stars burn more slowly and can last for billions or even trillions of years, over millions to billions of years. Stars fuse progressively heavier elements in their cores. In stars like our Sun, fusion stops at helium, and they eventually expand into red giants, shedding outer layers and leaving behind a dense core called a white dwarf. More massive stars undergo a series of fusion stages, up to iron, when fusion can no longer sustain the star's core. It collapses, triggering a supernova explosion, one of the most energetic events in the universe. Supernova scatter enriched material into space, seeding future generations of stars and planets with elements like carbon, oxygen, and iron building blocks for life. The remnants of these explosions can become neutron stars or black holes, exotic objects with extreme densities and gravitational fields. Stars also influence their surroundings by emitting powerful winds and radiation, shaping the interstellar medium and sometimes triggering new waves of star formation. Understanding stellar evolution helps us trace the cosmic cycle of matter and energy, revealing how the universe transforms over time through the light of stars. Astronomers measure distances, ages, and the chemical composition of galaxies. Stars connect us to the cosmos, for within them lie the very elements that make up our planet and ourselves. Chapter 18: Black Holes, Cosmic Mysteries of Gravity and Space-Time. Black holes stand as some of the most fascinating and enigmatic objects in the universe. Invisible yet powerful, these cosmic phenomena stretch the very fabric of space and time, challenging our understanding of physics and the nature of reality itself. What is a black hole? At its core, a black hole is a region in space where gravity is so intense that nothing, not even light, can escape its pull. This happens when a massive amount of matter is compressed into an incredibly small volume, creating a gravitational well with an event horizon, the point of no return. The concept of black holes traces back to the 18th century, when scientists like John Michell and Pierre Simon Laplace proposed dark stars whose gravity could trap light. However, it wasn't until Einstein's theory of general relativity in 1915 that black holes gained a rigorous theoretical foundation. Formation of black holes. Black holes often form from the remnants of massive stars. When such stars exhaust their nuclear fuel, their cores collapse under gravity, compressing matter to the point where the known laws of physics break down. This gravitational collapse results in a singularity, a point of infinite density surrounded by the event horizon. The singularity represents a frontier of knowledge, where quantum mechanics and gravity intersect in ways not yet fully understood. There are three main types of black holes. Stellar mass black holes, formed from individual stars, typically ranging from about 5 to 20 times the mass of our Sun. Intermediate mass black holes, hypothesized to have masses between hundreds and thousands of solar masses, potentially formed by merging stellar black holes or dense star clusters. Supermassive black holes residing in the centers of galaxies with masses millions or billions of times that of the Sun. The Milky Way harbors a supermassive black hole named Sagittarius ***. Properties and effects black holes are characterized: mass, charge, and spin. Despite their simplicity, their influence is profound. The event horizon is the boundary beyond which escape is impossible. Outside it, gravity warps space-time, causing phenomena like gravitational lensing, where light bends around the black hole, creating distorted or multiple images of background objects. Near the event horizon, the intense gravity slows time relative to distant observers, phenomenon called gravitational time dilation. Black holes also power some of the most energetic Phenomena in the universe. Matter spiraling into a black hole forms an accretion disk, heating up and emitting X-rays and jets of particles at near light speeds, black holes and information. Paradox, one of the deepest puzzles in modern physics, involves the black hole information paradox. According to quantum mechanics, information about a physical system cannot be destroyed. But classical black hole theory suggests that anything falling beyond the event horizon is lost forever. This contradiction has inspired decades of research, including Stephen Hawking's groundbreaking work showing that black holes can emit radiation now called Hawking radiations, slowly evaporating over vast timescales. Resolving this paradox may require a new theory of quantum gravity, a holy grail of theoretical physics. Black holes in the cosmos. Black holes play a vital role in shaping galaxies and cosmic structures. Their immense gravity influences the orbits of stars and gas clouds. Supermassive black holes may regulate star formation through energetic feedback, sculpting their host galaxies. Recent advances, like the Event Horizon Telescope's historic imaging of a black hole's shadow, have transformed black holes from theoretical curiosities to observable objects. Beyond the horizon, mysteries await despite great progress. Black holes remain shrouded in mystery. Questions about their true nature, their connections to quantum mechanics, and their role in the birth and fate of the universe continue to challenge scientists. They inspire wonder, inviting us to explore the frontiers where gravity, space, time, and quantum physics converge. Chapter 19. The Cosmic Microwave Background. Echoes of the Big Bang. One of the most profound discoveries in modern cosmology is the detection of the cosmic microwave background, or CMB, faint glow of microwave radiation that fills the entire universe. This ancient light is a relic from the very early moments after the Big Bang, a snapshot of the universe when it was just 380,000 years old. The birth of the cosmic microwave background. In the beginning, the universe was a hot, dense, plasma swirling soup of photons, electrons, and protons, all interacting intensely. Photons could not travel freely, bouncing off charged particles in an opaque environment. As the universe expanded and cooled, it reached a critical temperature around 3000 Kelvin. At this point, protons and electrons combined to form neutral hydrogen atoms in a process called recombination, with most charged particles gone. Photons were finally free to travel unimpeded. This release of light marks the surface of last scattering. The moment the universe became transparent, the CMB photons have been traveling ever since. Their wavelengths, stretched by the universe's expansion, now observed in the microwave region of the electromagnetic spectrum, discovery and measurement, the CMB, was serendipitously discovered in 1965 by Arno Penzias and Robert Wilson, who detected a persistent microwave signal coming uniformly from every direction in the sky. This discovery provided striking evidence supporting the Big Bang theory, overturning alternative models like the steady-state universe. Subsequent missions, including COBE, WMAP, and Planck satellites, have mapped the CMB with exquisite precision, revealing tiny temperature fluctuations at the microkelvin level. The tiny fluctuations, seeds of structure though remarkably uniform. The CMB shows minute variations in temperature and satrapies which reflect slight density differences in the early universe. These fluctuations represent the primordial seeds of all cosmic structure. Over billions of years, gravity amplified these tiny overdensities into galaxies, clusters, and the vast cosmic web. By analyzing the statistical properties of the CMB's anisotropies, cosmologists determine key parameters like the universe's age, composition, geometry, and expansion rate, polarization, and further clues beyond temperature. The CMB also exhibits faint polarization patterns, offering deeper insight into the early universe. One particularly intriguing feature, called B-mode polarization, could hold evidence for primordial gravitational waves, ripples in space-time generated during cosmic inflation. Rapid exponential expansion, thought to occur fractions of a second after the Big Bang. Detecting these signals would provide a unique window into physics at energies far beyond those achievable on Earth. The CMB as a cosmic Rosetta Stone. The cosmic microwave background acts as a cosmic Rosetta Stone. Translating the language of the early universe, it bridges the gap between theoretical physics and observable phenomena, enabling us to test models of the Big Bang, dark matter, and dark energy. It also constrains scenarios about the universe's fate, confirming a flat geometry consistent with an accelerating expansion dominated by dark energy. Endless horizons, the study of the CMB continues to evolve, with new experiments aiming to refine measurements and uncover subtle features as we listen to this faint echo from the dawn of time. We deepen our understanding of where we come from and the grand cosmic story unfolding around us. The cosmic microwave background is a silent witness to the birth of everything, a universal backdrop that connects us to the universe's fiery origins and its endless horizons. Chapter 20: Dark Energy and the Accelerating Universe. One of the most astonishing revelations in modern cosmology is that the universe is not just expanding. It is accelerating in its expansion. This discovery, made at the close of the 20th century, has fundamentally changed our understanding of cosmic destiny and introduced the mysterious concept of dark energy, the expanding universe. A historical perspective, the notion that the universe is expanding was first proposed in the early 20th century. Following Edwin Hubble's observations of galaxies moving away from us, with velocities proportional to their distances, a relation now known as Hubble's law. For decades, cosmologists debated whether this expansion might be slowing down under the influence of gravity, possibly leading to a future contraction or a big crunch. Others speculated the expansion could continue forever, but at a decreasing rate. Discovery of accelerated expansion in 1998. Two independent teams studying distant type Ia supernova stellar explosions, serving as standard candles for measuring cosmic distances, found something unexpected. The supernova appeared dimmer than predicted, indicating they were farther away than models with constant or slowing expansion predicted. This implies the universe's expansion rate is accelerating, driven by a repulsive force overcoming gravity on cosmic scales. What is dark energy? The unknown agent responsible for this acceleration was named dark energy, constituting roughly 68% of the total energy density of the universe. Unlike matter or radiation, dark energy exerts a negative pressure, causing space itself to stretch faster over time. Its nature remains one of the greatest mysteries in physics. Various theories attempt to explain it, including the cosmological constant, originally introduced by Einstein as a modification of his equations of general relativity to allow a static universe, later abandoned and now revived as the simplest form of dark energy, a constant energy density filling space. Quintessence, a dynamic field that changes over time and space. More exotic possibilities involving modifications to gravity or extra dimensions, implications for the fate of the universe. Dark energy's dominance shapes the universe's future. If it remains constant or grows stronger, galaxies beyond our local group will recede faster and faster, eventually disappearing beyond our cosmic horizon. This leads to a cold, dark, and lonely cosmos where star formation ceases and existing stars burn out. A scenario often called the Big Freeze. Alternatively, if dark energy changes over time, different cosmic destinies are possible. From a big rip where space itself tears apart, to more subtle evolutions, observational evidence, and ongoing research beyond supernova. Evidence for dark energy comes from the cosmic microwave background, large-scale structure surveys, and baryon acoustic oscillations, which all paint a consistent picture of a universe dominated by dark energy, upcoming missions like the Euclid satellite, the Vera Rubin Observatory, and the Nancy Grace Roman Space Telescope aim to refine measurements and probe the nature of dark energy more deeply. The philosophical and scientific challenge dark energy challenges our deepest understanding of physics, forcing us to reconsider the fabric of reality and the laws governing the cosmos. It sparks questions about whether the vacuum of space has intrinsic energy, how gravity operates on the largest scales, and whether new physics beyond the standard model awaits discovery. Conclusion: a universe full of wonder. Discovery of dark energy reveals that the universe is far stranger and more complex than imagined. It reminds us that even as we unlock cosmic secrets, profound mysteries remain, inviting humanity to continue exploring the cosmos with curiosity and awe. Dark energy stands as a testament to the evolving journey of science, from questioning to understanding, from observation to theory, and from wonder to discovery.